In this discussion, we will explore the chemistry of water. Water is a vital substance with unique properties that affect our daily lives and the natural world. Let's uncover the basics of water's chemical characteristics, starting with its composition.
Composition of water. Water chemically represented as H2O is a simple and essential compound composed of two hydrogen atoms and one oxygen atom. Here is some fundamental information about the composition of water. The chemical formula of H2O, two hydrogen atoms and one oxygen atom, are chemically bonded to form water. The molecular structure, water molecules are covalently bonded. The oxygen atom forms a double bond with one of the hydrogen atoms, resulting in a bent or V-shaped molecular structure. The molecular weight of a water is approximately 18.0 1528 grams of mole. The hydrogen and oxygen atoms in water are held together by polar covalent bonds. This means that electrons are shared unevenly, with the oxygen atom having a partial negative charge and the hydrogen atoms having a partial positive charges. Water can even exist in three states, on solid, liquid, and gas, depending on the temperature and pressure of the area. Water is known for its unique properties, including surface tension, capillary action, and the ability to dissolve a wide range of substances.
The structure of water. But before that, let's tackle the importance of water structure. One of the importance of water structure is that its unique structure. Its unique structure play a vital role in various chemical and biological processes. The second one is that it is a universal solvent. It is the one who's facilitating the dissolution of many substances. The third one is that it is water's high heat capacity. It helps to regulate temperature on Earth and in living organisms. So now, let's talk about the structure of water. One of the structures of water is the chemical formula. Remember, the chemical formula for water is H2O. This simple formula represents the composition of water at the molecular level. It tells us that a single water molecule consists of two hydrogen atoms and one oxygen atom. These atoms are chemically bonded together to form a stable molecule. Now, let's talk about the molecular structure of water. Molecules have a distinctive molecular structure. They are V-shaped, which is often referred to as a bent molecular geometry. This bent shape arises due to the arrangement of atoms within the water molecule. The oxygen atom is positioned at the center of the molecule. It forms covalent bonds with two hydrogen atoms, one on each side. Now, water is a polar molecule, which means it has an uneven distribution of electrical charge within the molecule. This polarization arises from the difference in electronegativity between the oxygen and hydrogen atoms. Electronegativity is the tendency of an atom to attract electrons. In a water molecule, the oxygen atom is significantly more electronegative than the hydrogen atoms. As a result, it pulls the shared electrons closer to itself, creating partial negative charges on the oxygen atom and partial positive charges on the hydrogen atoms. The polarity of water makes it a powerful solvent as it can interact with and dissolve other polar or charged substances. Additionally, this polarity is responsible for many of water's unique properties such as its high surface tension and its ability to form hydrogen bonds with other water molecules. These elaborations provide a more in-depth understanding of the chemical formula, molecular structure, and polarity of water, which are fundamental concepts in the study of water's chemistry.
A water molecule is electrically neutral, but its positive and negative charges are not distributed evenly throughout the group. The partially negative charge is concentrated at the oxygen due to its strong attraction to the unbonded electrons, leaving the hydrogen atoms with a partially positive charge. This distribution of charge makes the water molecule an electric dipole. Since opposite charges attract, the negative end of the water molecule tends to align itself close to the positive end of another molecule. Hence, water molecules attract each other wherein the hydrogen atom of one molecule pairs with the oxygen atom of another molecule. The lone pairs of electrons on the oxygen atom are attracted to the hydrogen in nearby water molecules. This dipole-to-dipole attraction forms a hydrogen bond, which occurs between a partially positive hydrogen atom and an electronegative atom with a lone pair of electrons. This hydrogen atom must be bonded with another electronegative atom such as oxygen, nitrogen, or fluorine. Water molecules are highly polarized, letting them form an extensive network of hydrogen bonds. Each water molecule can form a maximum of 4 hydrogen bonds, with the oxygen atom forming 2 hydrogen bonds due to its 2 lone pairs of electrons. The remaining 2 hydrogen atoms can form 1 hydrogen bond each. This extensive hydrogen bonding is responsible for its physical properties. When the water molecules crowd together as a liquid, their attractive forces have an obvious effect. In this phase, movements or heat will cause the molecules to move, generating kinetic energy enough to momentarily break their attraction, starting a cycle where hydrogen bonds are continuously being formed and broken as molecules slide past one another. When heat is raised, the higher kinetic energy of the water breaks the hydrogen bonds completely, allowing molecules to escape into the air as gas, which is steam. Due to its dipole-to-dipole attraction being weaker than a chemical bond, it is easily affected by ordinary thermal motions in its gas phase. On the other hand, low temperature freezes water, turning it into ice.
My name is Steven Andrew Sirakidan, and I'm here to present to you structure of ice. What is ice? Ice is a solid state of water that forms when water molecules slow down and arrange themselves in an ordered structure. As a result of decreasing temperature, water molecules with a chemical formula of H2O are polar due to having a positive and negative end. The polarity of water molecules allows for hydrogen bonding between them. So let's talk about property of ice. Let's start with molecular structure. What is molecular structure? Think of molecular structure as an intricate dance of atoms. They come together in a three-dimensional choreography, forming bonds and arranging themselves in a unique spatial design with a molecule. So let's talk about hydrogen bonding. What is hydrogen bonding? Hydrogen bonding is like a cozy group of hug, being a sociable atom, links arms with an electronegative pole, pulling in another friend for a warm, positive, negative embrace. Here's the 3 examples of nature ice information. Let's start with ice crystal. What is ice crystal? Ice crystal is a single microscopic piece of ice with a hexagonal lattice structure. It forms when water molecules freezes, arranging themselves in a unique and symmetrical pattern. Let's proceed to the second example, snowflakes. What is snowflakes? Snowflakes is a unique crystal formed as a water vapor freezes in cold air, creating intricate patterns in winter. Let's move on with our final example, icebergs. What is icebergs? Icebergs are massive floating chunks of ice killed from glaciers or ice shelves often found in the polar region. This is the 3 phases of ice. Number 1, solid phase. What is solid phase? Solid phase is the most recognized ice found in ice cube and snowballs. Number 2, liquid phase. What is liquid phase? Liquid phase is very familiar to us as the substance we drink and use to wash ourselves in objects. Number 3, vapor phase. What is vapor phase? Vapor phase is a water present in the air as the humidity and clouds and mist. Let's talk about artificial ice structure. Let's start with ice rings. What is ice rinks? Ice rinks is a frozen surface for skating, hockey, or recreational activities, typically indoors or outdoors. They are artificially chilled to maintain a solid ice layer, providing a venue for icy enjoyment. Let's talk about ice hotels. What is ice hotels? Ice hotels are accommodation made of ice and snow, featuring frozen architecture and furnitures. They provided a distinctive, ephemeral experience and frigid environment.
My name is Ian Canlas, and I will be joined by Alan Pascual to discuss the autoionization of water.
And I am Leonard Allen Michael S. Pascual.
Water can have a reaction with itself. Its molecules exchange protons with itself in very small amounts. The process is called autoionization of water.
Water is a molecule made up of two hydrogen atoms and one oxygen atom. It is a stable molecule, but it can sometimes break apart into two smaller ions, a hydronium ion and a hydroxide ion. This is called the autoionization of water. The autoionization of water is a chemical reaction in which a water molecule dissociates into a hydronium ion and a hydroxide ion. It is a reversible reaction and it occurs continuously in pure water. Here is a simple analogy to help you understand. Imagine a water molecule as a seesaw. The two hydrogen atoms are on one side of the seesaw and the oxygen atom is on the other side. The seesaw is balanced, but it can be tipped slightly to one side or the other. If the seesaw is tipped slightly to the hydrogen side, one of the hydrogen atoms will break up and become a hydronium ion. The remaining water molecule will become a hydroxide ion. If the seesaw is tipped slightly to the oxygen side, the oxygen atom will pull one of the hydrogen atoms from another water molecule. This will create a new hydronium ion and a new hydroxide ion. The autoionization of water is a continuous process. This means that the water molecules are constantly breaking apart and reforming. At any given time, there are a very small number of hydronium ions and hydroxide ions in pure water. The autoionization of water is important for many chemical reactions. For example, it is necessary for the formation of acids and bases. Acids are substances that donate hydronium ions to water, while bases are substances that donate hydroxide ions to water.
Water is considered amphiprotic, meaning that depending on the reactant, it can be either an acid or a base. Since it is amphiprotic, one water molecule can react with another to form a hydroxide ion and a hydronium ion in the autoionization of water. Next, properties of water. In the first equation, water acts as the base and the hydrochloric acid dissolves in water. It splits into chloride ions and protons. The proton then combines with a water molecule to create a hydronium ion. In the next equation, water acts as an acid and NH3 or ammonia acts as the base. It then receives a proton from water. Notice that the equation has a double arrow, meaning that the equation is an equilibrium reaction and has an equilibrium constant associated with it.
Acidic solutions have more hydronium ions than hydroxide ions. This is why they have a pH less than 7. The pH scale measures how acidic or basic a solution is, with 7 being the neutral. Strong acids have a high concentration of hydronium ions and a low pH. Weak acids have a low concentration of hydronium ions and a higher pH. Acidic solutions have more H3O positive ions than OH negative ions, acidic solutions of a pH less than 7, strong acids of a high concentration of H3O positive ions and a low pH, weak acids of a low concentration of H3O positive ions and a higher pH. Basic solutions have more hydroxide ions than hydronium ions. This is why they have a pH greater than 7. The pH scale measures how acidic or basic a solution is, with 7 being neutral. Strong bases have a high concentration of hydroxide ions and high pH. Weak bases have a lower concentration of hydroxide ions and a lower pH. Basic solutions have more OH negative ions than H3O positive ions. Basic solutions have a pH greater than 7. Strong bases have a high concentration of OH negative ions and a high pH, while weak bases have a lower concentration of OH negative ions and a lower pH.
The equation for the ionization constant is equal to the concentration of hydronium multiplied by the concentration of hydroxide. It can be calculated using both the hydronium ion and hydroxide ion when they are at 25 degrees Celsius. The pH level of pure water is equal to 7. When it is in pure water, the concentrations of both ions are equal to 1.003 times 10 raised to negative 7. Now that the values of the hydronium and hydroxide ions are known, the ionization constant can now be calculated. 1.003 times 10 raised to negative 7 multiplied by itself is equal to 1.006 times 10 raised to negative 14, or approximately 1.01 times 10 raised to negative 14. This is now the value of the ionization constant of water. When the concentrations of hydronium and hydroxide are equal, it is a neutral solution. In addition to that, if the concentration of hydronium is greater than hydroxide, it is an acidic solution. And if the concentration of hydroxide is greater than hydronium, it is a basic solution.
This shows the equation for the potential of hydrogen of a solution, where H positive is the concentration of hydronium ions in the solution. pH is a measure of how acidic or basic a solution is. A pH of 7 is neutral, a pH below 7 is acidic, and a pH above 7 is basic. The equation is based on the fact that the concentration of hydronium ions in a solution is inversely proportional to the pH. This means that as the ions increases, the pH decreases and vice versa. This equation is very important tool in chemistry because it allows us to measure and control how acidic or basic a solution is. The first equation is the definition of the potential of hydroxide, which is the measure of how basic a solution is. The second equation is the inverse of the equation, and it can be used to calculate the concentration of hydroxide ions in a solution, given the potential of hydroxide. Potential of hydroxide or POH is related to pH as their sum is always equal to 14. This is because water is amphoteric, meaning it can act both an acid and a base. This equation shows that pKW is the negative logarithm of the water autoionization constant Kw. Kw is the measure of the tendency of water to autoionize. The equation is simply a way of expressing the water autoionization in logarithmic form. It is a way of representing very large or very small numbers in a more compact form. It allows us to compare the water autoionization constant of water, to the water autoionization constants of other solvents.
Electrolysis of water. Let us start with some definitions of terms that will be used in this lesson. Electrolysis is the process of using electrical energy to decompose an ionic substance into its constituent smaller components. Electrode is a conductor typically crafted from graphite, enabling the passage of electrical current into the electrolyte. Anode is a positive electrode, while cathode is the negative electrode. Anion is a negatively charged ion that migrates towards the anode in electrolysis. Cation is a positively charged ion that migrates towards the cathode during electrolysis. Electrolyte is an ionic substance either in a molten or aqueous state, dissolved in water undergoing electrolysis. Electrolysis of water is using electricity to split water into oxygen and hydrogen gas by electrolysis. Electrolysis occurs in an electrolytic cell consisting of a positively charged anode and a negatively charged cathode. Hydrogen appears at the cathode, where electrons enter the water, and oxygen at the anode. In terms of volume, two times more hydrogen than oxygen is produced. Water electrolysis typically requires a potential difference of 1.5 volts, but with external heat it can be done with a minimum of 1.23 volts. How does it work? When the power source is turned on, electrons start moving from the anode to the cathode. Electrolytic substances break down into negatively charged anions and positively charged cations. These charged particles in the electrolytes help electricity flow. The positive cations move towards the cathode, where they receive extra electrons and become neutral. On the other hand, the negative anions move to the anode, where they release their extra electrons to become neutral. Eventually, this process results in the release of salts and gases at the electrodes. Now we move on to the chemical equation of the reaction that takes place in the electrolysis of water. In pure water, at the negatively charged cathode, a reduction reaction takes place, with electrons from the cathode being given to hydrogen cations to form hydrogen gas. At the positively charged anode, an oxidation reaction occurs, generating oxygen gas and giving electrons to the anode to complete the circuit. In order to balance each of reaction, the water needs to be acidic or basic. In an acidic solution, the reduction reaction that takes place is two hydrogen ions plus two electrons is reduced into hydrogen, and the oxidation reaction that takes place is two water is oxidized into oxygen plus four hydrogen ions plus four electrons. In a basic solution, two water plus two electrons is reduced into hydrogen plus two hydroxide ions, and two hydroxide ions is oxidized into 1 over 2 oxygen plus water plus 2 electrons. Overall, both solution results in the same reaction of 2 water is split into 2 hydrogen plus oxygen, which proves that twice more hydrogen than oxygen is produced. Here are some few applications and uses for the electrolysis of water. Hydrogen fuel. Hydrogen is a clean fuel that when consumed in a fuel cell produces only water. The hydrogen gas released by water electrolysis can be used as hydrogen fuel. About 5% of hydrogen fuel produced worldwide is created by electrolysis. Oxyhydrogen welding. Separately pressurized into gas tanks or bottles, the hydrogen can be used for oxyhydrogen welding and other applications, as the hydrogen-oxygen flame can reach approximately 2,800 degrees Celsius. Oxygen. Water electrolysis is used to generate oxygen for the International Space Station.
Water pollution occurs when our water sources become contaminated. This contamination has widespread consequences, affecting all living organisms that rely on these water bodies. Water pollution primarily arises from the introduction of toxic chemicals and waste products. Often originating from industrial and agricultural activities, these pollutants lead to water contamination. This poses serious threats not only to humans but also to the entire ecosystem. The harmful substances from these pollutants can make their way up to the food chain, eventually affecting humans. While the damage is usually concentrated at the local level, it can have global implications. Each year, approximately 6 billion kilograms of garbage is deposited into the oceans. Various unwanted materials from nuclear waste to oil spills contribute to making vast areas uninhabitable. The impact of water pollution varies depending on the type and concentration of pollutants and the proximity of water bodies to the areas. Water bodies near cities are particularly affected due to the disposal of garbage and toxic chemicals by industrial and commercial establishments. The consequences of water pollution extend to various aspects of the environment, particularly within the food chain. Toxic substances like cadmium continue to disrupt ecosystems at higher trophic levels. Humans are not immune to these consequences and can contract diseases such as hepatitis through exposure to contaminated water sources. Inadequate treatment of drinking water and the presence of unsafe water can lead to outbreaks of infectious diseases. Moreover, water pollution can have a profound impact on ecosystems, causing critical modifications and disruptions in the environment.
As we all know, the water pollution is a serious environmental problem with grave consequences for ecosystems, public health, and the economy. So, here are the following possible solutions to combat water pollution. First, improve industrial practices. Industries can reduce water pollution by implementing cleaner production techniques, recycling and reusing water, and properly managing hazardous materials. This helps minimize the release of pollutants into water bodies. Second, clean up and remediation. In cases where pollution has already occurred, cleanup and remediation efforts may be necessary. This can involve removing pollutants from the water, restoring ecosystems, and rehabilitating contaminated sites. The third one is research and monitoring. Continuous monitoring and research help identify pollution sources and trends. This data can inform policy decisions and guide efforts to address specific water quality issues. The fourth one is technological innovations. Advancements in technology can provide innovative solutions for water pollution. These include the development of new water treatment methods, monitoring devices, and early warning systems. The last one is public awareness and education. Raising awareness and educating the public about the importance of clean water and the ways to reduce pollution is crucial. Informed citizens are more likely to support and engage in water protection efforts.
Rising sea levels are a global problem with severe um, effects for countries like the Philippines. This issue is a significant concern for several reasons. Firstly, rising sea levels pose a direct threat to the world by endangering coastal communities, infrastructure, and ecosystems. Coastal flooding and erosion becomes more frequent and severe, resulting in widespread damage, displacement of populations, and economic losses. Secondly, the Philippines, an archipelagic nation with numerous coastal communities, is particularly vulnerable. As sea level rises, these communities face heightened risk of flooding, erosion, and saltwater intrusion into freshwater sources, affecting millions of people. Additionally, the Philippines' rich biodiversity and coastal ecosystems are under threat. Mangroves, coral reefs, and wetlands that support marine life and protect against storm surges are at risk of degradation and destruction. Furthermore, as sea levels continue to rise, there are broader societal and economic challenges. Access to drinking water, agricultural stability, and food security become more difficult. Rising sea levels result from two major factors linked to global warming: the melting of glaciers and ice sheets, and thermal expansion of seawater. Firstly, due to global warming, glaciers and ice sheets are rapidly retreating, losing nearly 30 trillion tons of ice between 1994 and 2017, and melting at a rate of 1.2 trillion tons each year. The significant ice loss is a major driver of rising sea levels, accounting for 21% of global sea level rises between 2000 and 2019. Secondly, there's thermal expansion, where seawater expands as it absorbs heat due to global warming, increasing the space between water molecules. This process significantly contributes to rising sea levels, responsible for about 50 to 75% of 20th century sea level rise. And in conclusion, these two processes, glacier and ice sheet melt and thermal expansion, are the key factors behind rising sea levels, posing a substantial threat to coastal communities worldwide. Addressing global warming is crucial to mitigating these effects and safeguarding our coastlines. Rising sea levels brings three major challenges to coastal regions: coastal flooding, coastal erosion, and saltwater intrusion. Firstly, the coastal flooding. Higher seas lead to more frequent and severe flooding along coastlines. This flooding damages homes and infrastructures, leaving communities in distress. As the threat grows, people often have to leave vulnerable areas, searching for safer ground. Second is the coastal erosion. Rising sea levels also mean that the sea nibbles away at the land, a process known as coastal erosion. This erodes the coastline, harming wildlife and ecosystems while making coastal regions less stable and secure for both people and nature. And lastly, saltwater intrusion. The rising sea can mix with freshwater sources in coastal regions, leading to a big problem. It makes drinking water salty, and it also damages farming by contaminating the soil and water. So finding clean drinking water and growing food close to the coast becomes a serious challenge. So to sum it up, rising sea levels pose a very bad threats, leading to coastal flooding, erosion, and saltwater intrusion, with significant consequences for coastal communities, ecosystems, and agriculture. Even our even the country's economic state could also be affected. Addressing rising sea levels requires a multifaceted approach to protect our coastal communities and the environment. Here are three key strategies. First, future-proofing. We need to develop and fund plans and projects that adapt to rising sea levels. This includes building protective structures like seawalls, reimagining the way we design roads, and strategically planting vegetation like mangroves to absorb water and reduce the impact of flooding. Second is to raise awareness. It's crucial to inform the public about the challenges posed by rising sea levels. This awareness empowers people to actively participate, contribute, and support projects and policies aimed at tackling this problem. Despite the overwhelming evidence provided by credible sources, there are still individuals who deny the existence of this issue. Raising awareness helps change that. Finally, combat climate change. The primary driver of rising sea levels is climate change, particularly the melting of glaciers and ice sheets. To address this, we must take comprehensive action to minimize climate change. This includes reducing greenhouse gas emissions, transitioning to clean energy sources, and supporting policies and international agreements that promote a sustainable and environmentally friendly future. Um, Future-proofing, raising awareness, and combating climate change are essential steps in the fight against rising sea levels, ensuring a safer and more secure future for coastal regions and our planet as a whole.
That is all for our presentation. Thank you for listening.